I want to introduce what originally would have been our first presenter here. So, who is joining us online? Pierluigi Da is a tenure-track assistant professor of structural design at the School of Engineering and Design of the Technical University of Munich, TU Munich. He graduated with honors in building engineering architecture from the University of Pisa in 2007 and received a Master of Architecture with distinction from the Architectural Association School of Architecture in London in 2012. In 2018, he completed his doctorate with distinction at ETH Zurich. Since 2006, he has gained professional experience in various architecture and engineering offices in Italy and Switzerland, and has been awarded in several international architectural competitions. From 2012 to 2018, he was a research assistant at the Chair of Structural Design at ETH Zurich, and from 2018 to 2021, a postdoctoral researcher and lecturer. Pierluigi's research explores the convergence of architecture and structural engineering through computer-aided design in emerging construction technologies. His research interests are geometry-based methods for structural design, computational design through equilibrium models, structural form finding with machine learning, and fabrication-aware structural design using advanced digital manufacturing. His topic today will be human-machine collaboration for conceptual structural design. Let's please welcome Pierluigi.
Thank you very much. So thank you very much for the very kind introduction, and it's a pleasure to be here at the conference. Unfortunately, I have to apologize. I was not able to fly to Florida, as here is quite busy time here in Munich for the start of the semester. So I didn't really manage to find the time to be there in person. There's pity because I see that it's a great environment, also a nice discussion. But I hope it will be also fine to be online and to be able to discuss with you about my work and all the discussion about this human-machine collaboration in my case in structural design. I see in the case of all the other presenters in many other fields of architecture and engineering. So I share my screen so we can get started. Okay, I think you see my screen. So, the talk today is about specifically the point of view of structural design in the use of artificial intelligence. And specifically, the idea is to put forward and to share with you some of the recent research that I developed here at the Technical University of Munich, but in reality, this is all work that has been started when I was still at ETH Zurich. And specifically, a very much and very big part of this work is collaboration and ongoing collaboration that I'm carrying out together also with Carla Saldana at the University of Florida. Well, I would like to start my presentation with this quote by the structural engineer Sergio Musmeci. And Sergio Musmeci is a structural engineer from the second half of the 20th century from Italy. He was a very special engineer because he was very much devoted to the developments of new methods in terms of building and designing new structural forms. Musmeci says that this is in 1972. When we speak of the use of electronic calculation in the field of structures, we generally refer to the enormous possibilities it offers in the verification of the stability of very complex structures. I want to take for granted these quantitative aspects of the use of the computer and draw attention instead to the qualitative effects that its diffusion may have and almost certainly will have in the field of structural design. These effects can be considered as the results of the interaction between the machine and the human inventive capacities and are bound to grow as humans learn to use the machine to explore ever wider fields of possible solutions. So this is quite interesting that is coming from a structural engineer. A structural engineer, as I said, is a very special one You may know some of his work, and specifically these very outstanding and amazing projects. This is a BILS project in the south of Italy. The Ponte sul Basento is a bridge, a highway bridge that is connecting the city of Potenza in south of Italy with the highway. And this bridge actually was developed with quite a lot of effort in terms of the fabrication, but was designed with very innovative methods. And we see in these slides some of the methods that were used by Sergio Musmeci to design the bridge, very similar to methods developed in the same years in Germany by Frei Otto, for example. So you see on the left side, there are some models. These were developed with soft films in order to generate a minimal surface that is spanning in between the boundary condition that is represented by this wireframe metal structure. We see in the top of the slide a meta-acrylic model. This was designed and developed in order to do structural tests. And we see in the middle some drawings, and these drawings are actually one of the first representation of the use of the personal computer in order to generate form through the method of form finding. So developing a code that is able, given certain boundary conditions, to reproduce the same geometry that can be developed with the physical models like the soft field model on the left. And this is a very, very early application of the computer for generating new structures. And it's very interesting to read also in the text of Musmeci that at that time when the computer was very much used still in the early days in structural engineering, mostly to verify the stability of structures. In his case, he was already foreseeing the use of computer for generating new structural forms that are going beyond what everyone was assuming in terms of conventional structural typologies. Unfortunately, Musmeci was not able to really make use of computers and explore the potentials of the computers because he dies a few years later. Well, this is to introduce the idea of the computer as a generative tool in order to use the power of the computer not just to analyze a predefined form, but rather to generate new structural form. Well, when we go into the digital age, and we talk about the digital age, obviously the role of design is very prominent. And in these respects, what is quite interesting in terms of the framework around the digital age in relation to the design and the theory is these inputs by Rivka Oxman that's introduced somehow and try to develop a kind of a framework in order to define the different ways how the human designer is getting into contact with a computer and using the machine in order to perform design-related tasks. So we see here in this diagram, she postulated the idea of having the human designer in the center and then different possible operations that are somehow representing all the operations that are typical in a design process: the representation, the generation, the evaluation, the performance. In terms of the way how the designers is interacting with these different operations, then it is possible to define different types of design-based models. In certain cases, the interaction is very implicit, so there is not a direct real-time interaction with the tools and the means of representation. In other cases, the interaction is directly explicit, and in this case, there is a full engagement between the human and the machine. So a very typical model, the very simple model is the so-called paper-based model, in which all the phases of evaluation, performance, and generation are somehow implicit, and the designer is interacting with the means. So the paper-based model is taking advantage of the tool in order to represent the actual design, but not too much to perform the other operations. This somehow is typical even in the basic approach to design. We see here a nice picture of the SOM office in Chicago, and this is from the 1958. And this was obviously at that time the only way how designers were able to interact with the design. So representing something on paper and then modifying this in order to slowly converge to the design, the final statement for the design. In this case, obviously, the interaction is very somehow is very not direct and requires several iterations, and it is not possible to have this one-to-one and interactive real-time interaction with the tools. The next step would be the introduction of the digital tools that allows for this more real-time use of the tools and transformation of the design in such a way that is possible to incorporate a more feedback between the human and the digital model itself. Obviously, in the first place, in the basic case, this interaction is minimal. So the tools, the computer is used mostly to represent, somehow as a replacement of the paper. And the tool is used for drafting, but not really to engage into the operation of exploration of different design options, generating different options and evaluating the performance of the design. Typical, obviously, in this case, example would be the Sketchpad that was developed by Sutherland. And obviously here we see already a first way how the human and the machine are coming together, with a human that is able to, in real time, adjusting the geometry of the structure. And very interestingly, we see in this example, it is indeed a truss structure that is shown on the screen. And by having this model, it is possible to evaluate the internal forces in the structure, but still the interaction between the human and the machine is quite limited. Another quite relevant design model, especially from the point of view of structural design, is the so-called performance-based model. In this case, the machine is also used in order to run certain performance evaluations, and this is used as a feedback for the designer in order to adjust the design itself. Here, for example, we see a typical finite elements model that is used in order to evaluate and analyze given structures. Obviously, also in this case, the interaction between the human and the machine is quite limited in a way that the model is loaded into the software. The software is evaluating the structural performance of the given model in terms of the stresses or the deformations, and then is providing a feedback to the user. And the user can, in a quite indirect way, define where the parts of the structure are not working, where there are peaks of stress or deformation, and then try to adjust. Also in this case, again, this is a quite static model. There is not, or the machine is not really used in order to suggest variations or even to generate new variations of the design at once. Obviously, ideally, a model that is taking into account all these steps and there's a quite direct interconnection between the human and the machine, that would be the so-called compound model, and this would allow a full integration between the different design operations within the same workflow in such a way that the human and the machine can collaborate together within the same design process. This somehow we will see later what we try to attempt by merging our methods and tools for structural design with the use of artificial intelligence. Before we get into this, actually, I would like to give a bit an overview of what are the methods that we use for structural design. So we use methods that are in this for generative structural design. That means develop form from scratch structural form from scratch that perform in terms of the structure, but also obviously integrating other aspects, like, for example, architecture-related questions. And to do this, we see that the most powerful way to generate new structural form is indeed to work at the same time with form and forces. And this is a typical approach of structural design that was very much used in the past, and nowadays is somehow was getting lost, somehow has been rediscovered since a few years. But if we look back in the past, actually, and in the past, I mean a very long time ago, in the first half of the 18th century, this was a typical approach to understand how structure works and how to make use of the form of a structure to be able to tell how the forces should flow within the structure. And this is very much related to the disciplines of graphic statics. So graphic statics is a discipline that was initially developed in the first half of the 18th century that links directly form and forces. And we see here one copy of the book of Varignon, and in here we see all these drawings, and these drawings are representing cables that are put in equilibrium by adding different masses. So the masses on appended hanging from the cables, they enforce the cable to take a very specific shape, and this is a shape that makes the cable that is infinitely flexible into equilibrium. So you might have studied this also, some of you at the high school, and the principle is very simple. Given a structure in equilibrium like the cable on the left, it is possible to represent the equilibrium of the structure with graphical means, and specifically with this diagram that we call the force diagram that we see on the right. So we take a structure in equilibrium. That means that each and every node of the structure is itself in equilibrium. But that means that if we consider one node of the structure and the forces that are applied to it, in this case, it would be the weight of the mass and the forces that are inside the cable that is put into tension by the mass. These three forces can be combined in such a way that they close a polygon we see on the right. So this is the so-called force polygon. This is nothing else than the principle of vectorial addition. In order to have equilibrium, the three forces should cancel each other, and they cancel each other when they close this triangle of forces. The peculiarity of the force diagram that we see on the right is that we can measure the lengths of these vectors in the force diagram. These are proportional to the internal forces. So this tool is a very, very simple but very powerful tool that allows us to control at the same time form and forces. Obviously, we can repeat the same construction for each every node of the structure until we get to the both final form and force diagram. Now, what is interesting here is that this tool, we will see later, can be used not just to analyze how big are the forces inside the structure, but also as a generative tool in order to transform and generate new structures that are by definition in equilibrium. So graphic statics was used very much at the end of the 19th century and developed into an autonomous discipline. And this was mostly thanks to the contribution of Professor Karl Kuhlmann from ETH Zurich that collected all the geometric constructions of graphic statics into the graphische Statik. That is a book that's integrating all structural engineering construction using graphical methods. We see here, for example, the design of a suspension bridge on the top of the slides and the corresponding force diagram below. And this, very interestingly, has been then developed very much into mathematical formulation, especially in projective geometry. And this was very much thanks to the contribution of Luigi Cremona from Italy in also 1872, and the very famous scientist James Clerk Maxwell that both develops a projective geometry-based method in order to generate at once these two form and force diagrams. Now I'm showing this because actually quite a big and important part of my research was, and it is, to take this knowledge and bringing it into contemporary computational environments. And this was developed by introducing the so-called vector-based graphic statics. And vector-based graphic statics, together with other methods of other researchers all around the world, tries to take this knowledge of graphic statics and all these constructions that at that time were performed on paper. So it was very much tedious. For every transformation of a structure, it was necessary to rebuild manually all the form and force diagram. This is brought into a computational setting that allows a real-time operative transformations on the form and force diagram. And on top of this, thanks to the use of three-dimensional software environment, it is possible to bring all the construction from 2D to 3D. So you see here, for example, this is a so-called tensegrity structure on the left. So we see in blue, we use to delineate elements of the structure that are in compression, in red in tension. And by developing this approach of vector-based graphic statics, given a form in equilibrium, it is possible to generate a corresponding force in equilibrium. This, I will skip the detailed explanation, but is working very much using rules based on graph theory. So first of all, we generate the topological representation, so the graph of the structure, and based on this, we are able to generate the different force polygons, as we saw before in the case of Varignon, and assemble them in one unique force diagram. Obviously, thanks to the use of computational three-dimensional environment, it is possible then to operate transformations of the structure, so transform the form and the forces at the same time. This allows, for example, to accommodate various requirements that are coming from architecture, for example, in terms of the form, but at the same time, accommodates requirements coming from statics. So, for example, try to reduce the internal forces, that is, try to reduce the necessary amount of materials for the builds and construction of the structure. Obviously, this can be extended to much more complex structures like this tensegrity structure that we see here, and also three-dimensional systems that are self-stressed, like this two form and force diagram. Interestingly here, either one or the other can consider as a structure in equilibrium. For example, if we take the force diagram on the right, it's by itself a structure in equilibrium, its force diagram would be the form diagram. This is because of the reciprocity between form and force diagrams. And this principle, that is equilibrium, that is a basic principle, can be applied to any scale, any material, obviously with certain constraints, but potentially any kind of structure system. We see here, for example, this cable nest that is in tension. Here, a compression-only dome that is somehow inspired by a project by the engineer Pierluigi in Ervil, Palazzetto dello Sport in Rome. Here, for example, a combination between this spiraling pattern in compression with this ring in tension. You see again form and force diagram. And at the same time, it is possible to operate transformations that are constraints. For example, here we see the design of this suspension bridge, and we constrain certain elements of the force diagram in order to have the same force in the suspension cable. Now, this works directly with form and forces. In parallel developments of our research with colleagues at ETH Zurich and now here at TU Munich, we introduce a new dimension to these developments and design of structures, especially with the combinatorial equilibrium modeling. And this new dimension is actually like making a step back and operating directly on the topology of the structure. And the topology of the structure represents in a very simplified diagram, a 2D diagram, how the elements of the structure are connected to each other and what is the combinatorial state of the internal forces in terms of tension and compression. So given this diagram on top that we see here, we can assign a certain connectivity of the different elements, and based on these connectivities, using the combinatorial equilibrium modeling methods, it is possible to derive form and force diagram. And obviously, as a designer, one could operate at this point, not just on form and forces, but directly on the topology of the structure. And this, as I said before, opens up a new dimension in the exploration of different structural possibilities and different structural options, because as we see here, given the initial same ground topology, it is possible to start to test different ways how to connect the elements within the structure and assign different patterns of tension compression. And for each and every of these topology, it is possible to apply different metric variation in terms of the size of the element or the forces, the magnitude of the internal forces. And this allows to having in a very complex and quick way quite a broad range of possible structural variations. This obviously can be used to explore different possibilities to solve the very same initial problems. Like we see here, the same topology is conveyed into different form diagrams. So these are shell structures, tension and compression seen from top. And this can be applied to any kind of structural system, because we are working with equilibrium principles that are the same in every kind of structural system. That is, we can operate with these tools in order to design new bridges, like we see here, pedestrian bridges that are hybrid system in between conventional typologies, like an arch bridge, like the one in the top center, that is mixed up with a cable stayed bridge, or many other systems that are very much going beyond the usual structural typologies. Here we see the same tools applied to the design of large span roof structure like this stadium. And again, by having a small and very simple quick variations on the topology of the structure and the assignment of tension and compression, it is possible to explore completely different solutions. Here, for example, the same approach applied to the design of the load-bearing structure of a building, going beyond the classical approach of the columns on slabs and try to redirect and manipulate the internal forces to accommodate, for example, requirements coming from architecture, like having more open space, more generous spaces, double level spaces, or try to compact all the load-bearing structure in a certain portion of the buildings. Well, given this now, the question is how can we control this all this variability of different options and parametric models that opens up the possibility potentially to generate thousands and thousands of structural design options for the same given initial brief and problem. And this is the way we try to address this is by introducing in the conceptual structural design the use of machine learning. And this is a first attempt that we made, actually, a project that we developed when I was at ETH Zurich together with Carla Sardagna and other colleagues. And the goal here was very much about thinking beyond the typology. So going beyond the idea of having clear structural typologies to follow, and also going beyond the idea of optimization. Another way that is a common use of computers in structural engineering is to optimize. So give a certain boundary conditions and then try to minimize a certain quantity. Obviously, that is very relevant in terms of structural engineering, but not so much in terms of structural design. So starting with a very open brief, designing a bridge that is connected to points, obviously in the first place, in the conceptual phase, is interesting and very important to test completely different variations. So we used this approach in order to make a way that's to simplify somehow the phase of the exploration of the different structures that can be generated now with the tools that we saw before by using the machine learning supports, like we see here, the building that I was showing before. And this is somehow a framework that we developed very much inspired by the framework that we saw before, introduced by Rivka Oxman, but somehow introducing this idea of the collaboration between the human and the machine. So having the possibility that the human and machine are literally collaborating as different designers within the same design task, using the power of the machine that is able to handle a large amount of data and making calculation and computing very fast, but also combining these with the qualities of the human designers that are very much about the creativity of thinking outside the box. And well, we then built up this framework in such a way that we readapted somehow the categories that were introduced in the previous framework by Oxman in order to adapt them better to the use of the machine, especially machine learning processes within the design process. And we see here that obviously the same operation of generation of the design options, the evaluation, in this case, separating the quantitative evaluation, the qualitative evaluation, because they're performed by the two actors in the process, in one case, the human, in the other case, the machine, and then the clustering operation that is used in order to allow the human designer to be able to grasp this huge design space of possible solutions. Obviously, the design process is not linear, it's not sequential. Each of these operations can be performed in a non-sequential way, repeated several times in a non-linear fashion. So we tested this in a quite basic setup. Again, in the first place, in order not to open up too much the design possibilities, with a ground topology that was defined. And the test was applied to the case study of designing roof structures. We see here on the left the topology, and on the right some instances of the design options. This was developed by using a parametric model, using the combinatorial equilibrium modeling, and then letting after setting specific ranges of the input parameters, letting the model generating structures, randomizing the setting of the different parameters. What is quite important to say is that all structures that are generated, since they are built with this quite robust method, the combinatorial equilibrium modeling, are all structures that are in equilibrium. Some of them, from a formal point of view, may be non-completely reasonable in terms of their possibility to be actually constructed, but they are all structured in static equilibrium. Obviously, what's happening is that by having this large number of input parameters and the possibility for each parameter to range in between different options, the design space is very large, and there is a multi-dimensional design space, one dimension for each parameters. And the problem obviously becomes for the human designer to be able to grasp this design space and to navigate into this design space, even because obviously some of the parameters, they perform in a non-linear way. So it's not possible just to control one parameter at a time and assess a linear transformation of the structure. And because of this, we introduced a machine learning model that is the self-organizing map. This is a self-learning model that is able to, given these inputs that is the design space of structures that are generated by the combinatorial equilibrium modeling. The model SOM is able to cluster the structures according to input criteria that are defined by the user. And in this case, for example, we define as an input criteria the similarity in forms of the structure. That means that the self-organizing map methods was checking the similarity in terms of the position of the coordinates of the position of the nodes and the coordinates of the nodes of the structures, and then clustering all the structures according to this, which ended up in this map that is a 2D map, 40 by 40 map that shows 40,000 structures concentrated into this one map. This, in the first place, is used in order to create a more intelligible map or visualization of the design space. Each of these cells is actually containing a certain number of structures from the original design space that are all clustered within that cell because they are all similar in form. On top of this, on the right, we see the possibility to map specific performative criteria. For example, in this case, we see the load path that is a measure of the performance of the structure. And this is done on top of the map in order to allow the human designer now to be able to navigate within the map, check the different structural solutions, and then make an evaluation of the structure, qualitative evaluation. In the same time, it is possible to apply a quantitative evaluation that is done directly by the machine. And this would lead to the possibility of the human designer to narrow down the design space from the initial 40,000 structures to a more limited amount of structures. And this can be done by selecting and discarding certain design options. What is interesting is that at this point, once structures are labeled as 1 or 0, either selected or discarded, this can be encoded into a new model. For example, in this case, we were using a gradient boosted tree model that is another machine learning, this scaled supervised model that allows to learn these preferences in the selection of the structure by the human designer, and then potentially rebuilds and regenerates a new structure that are most likely falling within the structure that the human designer would select. And after this, the machine is able to reproduce and produce new structures that can be then again assessed by the human designer. And obviously, as I was showing before, this process can be iterated as many times as possible, narrowing down the design space and then opening up again. Here we see 3 of the structures that were generated by these methods, completely unusual structure. And we see this one in the video, something that we would never come up with in the first place if we have our, let's say, bounded to our experience of existing structures. This method obviously was very much applied to structural design, but it's a general method, can be applied to any kind of other disciplines. We made also a test to connect the design, the structural design with other technology-driven aspects. For example, in this case, aspects related to building physics, like the solar exposure of the building during the, in terms of the penetration of direct sunlight into the structure. And this, for example, was made by incorporating other algorithms on top of the combinatorial equilibrium modeling within the design workflow. We made a quick test in this case study by designing structural facades that at the same time were working also in terms of shading. And we see here, again, the self-organizing map here, in this case, 60 by 60 nodes, 26,000, around 26,000 design options. And again, the possibility for the human designer to navigate within this design space in order to define the next step in the design process. Here we see some of the options that are connected to the design process that we saw before. Well, this is somehow the basic framework we developed also together with Carla. The next step was in our, let's say, collaborative research was to try to see how to enhance also the interaction between the human and the machine. So in our next step of the research, and this is still an ongoing project, we are incorporating the possibility to introduce a direct way how the human designer can interact with the machine, specifically working with text prompts. So you are very much familiar with all the developments in the last few months in terms of the use of large language models like ChatGPT. So the idea in our approach would be to also make use of this possibility to communicate and interact with the machine using text prompts. But in this specific instance of research, we have the backgrounds of all the other tools that I was showing before and the framework that we developed before in such a way that the design is not just generating random forms, but the machine is able to generate forms that are always in equilibrium, in static equilibrium, and they fulfill not only qualitative goals or criteria, but also at the same time also quantitative criteria. So it's really about trying to merge the creativity of generating new forms with also the possibility to control the performance of the structures. And here we see a workflow that we developed, and we are still developing. This is work in which we have the generative phase at the beginning. Again, this using the combinatorial equilibrium modeling to generate the structures in equilibrium. And then we have a first step of evaluation in which we can also integrate other methods like the finite elements method in order to evaluate certain performative criteria and parameters of the structures. And then this goes into this process of filtering. We have a first step we see in the second column of the flowchart that is about the quantitative filtering. And this is about casting in putting hard constraints, casting out of the design space all those structures that are infeasible in terms of certain structural criteria. For example, structures in which the internal forces are exceeding the capacity of the materials, or structures in which certain parameters they render the structure not feasible to be constructed. And after this filtering, and this is done together with the machine can control this quantitative filtering. There is a second step of qualitative filtering. This is similar to what we saw before. So the self-organizing map is used to cluster the multidimensional design space in something that is intelligible by the human designer, and the human designer can start to operate on the design space that is rendered in such a way that is readable. After this filtering, then we go into the phase of labeling. So the human designer and the machine at the same time, they can place and put labels to the structures. These labels can be either related to qualitative aspects of the design, so how the structure look like, and this would be done by the human designer, or other labels can be pure quantitative labels in terms of the performance, in terms of specific parameters. And then this is all put together into a short textual description of the structure. So each design option, each structure would be described in terms of a paragraph that is combining these qualitative and quantitative features of the structure. And then this goes into the last part. We see here the training data generation, in which we use the combination between the vector of the structure with a paragraph describing the structure itself will be everything embedded into a natural language processing model that is able to create text vector embedding, so linking the two things together. And by doing this, we then introduce a GAN model that is training, and the trained model then can be eventually go back and linking the outputs with the input parameters. So this is what is done on the side of the developers of this data set of structures. And then once after the training of the model with the GAN, this data set can be deployed to the human designers that are able then to use this in order to make a text prompts and then retrieving automatically new structures generated using the initial inputs. So we see here some tests with this at the level of high-rise structures, again, the topology and the form. And here we see the sum with different types of structures. Here again, different sample from the initial data sets. And then here the phase in which we introduce the labels to assign a specific qualitative connotation and features to the structures. And this is done on top of the sum, and the human designer is able to assign specific labels to specific parts of the sum by using this graphical interface. What's happening in the end is that when the human designer is then adding a text prompts to the model, for example, asking for structures that are thick and heavy, like we see in the top left, then the model is able to produce those structures as most likely are linked to what was labeled in the data set as thick, as heavy. Obviously, by using a natural language process, it's also possible to go beyond the specific label and write generic sentences, not necessarily using the keywords that were used for the labeling, and the model is able to link directly the text prompts to the structures that are generated within the system. So this is somehow where we are now. Now we are working together with Carl and other colleagues to try to make this process much more user-friendly and being able to deploy it as an open source software, so that either architects or structural engineers can then use this in the very early conceptual phase of the design. Okay, so that's it. I would like now to close my talk with this, again, going back to Sergio Musmeci. He says, it is obvious that the computer can be of great help in the verification phase, but on the other hand, it is also evident that only if a way is found to use it also in the first phase at the service of the inventive capacities of the designer, will it be possible to ensure that it can contribute to the research and creation of new and more efficient structural forms. I believe that one day, perhaps not very far in the future, this will be the way of designing for a creative structural designer. The automatic calculation, far from limiting their imaginative possibilities, will represent efficient support for them, as well as powerful means of amplifying their impacts on reality. Somehow the motivation of our research is very much about taking advantage of this possibility of collaboration between the human and the machine to open up new imaginative possibilities and enhance the creativity also in fields like structural engineering that usually are very performative driven. So thank you very much, and I'm very happy now to answer your questions and discuss with you.
All right, Pierluigi, would you stop your share screen, please?
Yes, yeah.
Thank you. And we can take any questions from the floor. Ricardo?
Can you hear me? Can you hear me?
No. Maybe it's maybe easier to come to the podium to ask questions. We'll have a line here.
Can you hear me now?
Yes,
Okay,
yeah,
great.
I can hear now.
Yeah,
Thanks.
thanks for your presentation. I was wondering, so you showed something which was based as, let's say, structural. I mean, I'm not a structural engineer, so I'm an architect, but I'm a bit alien to the field, so take everything with a grain of salt. But you showed something which is related to structural engineer, which is a discipline which, of course, goes well hand in hand with calculus and with physics. And so it kind of lends itself quite nicely to fit also in working together with computation, as also you were showing with Musmeci. But I was wondering, so at the same time, what I also appreciated a lot in your presentation was all, let's say, the more historical look with also these references, for instance, such as Nervi, no? And I was wondering if you could think of machine learning applied in these fields also as a way to, if it would be possible to use it also to learn from this example of the past, you know. So for instance, you know, Nervi is precisely, I would say, beyond optimization. So to kind of cultivate a certain data set, I don't know how to call it, but a certain archive of things that, or examples that are interesting precisely because they go beyond optimization, and try to use it as a way to, let's say, invent solutions that are not necessarily new from a formalist point of view, but they somehow re-articulate this, like, let's say, great heritage of the past. That would be my curiosity.
Yes, thank you very much. Actually, it's a very, very good question. And indeed, it's really very much about learning also from the past. And you see, you know, my presentation and my research is very much about learning from the past and try to reuse and reinterpret certain methods and tools from the past in a more contemporary way, making use of the technology and the possibility that we have nowadays. And indeed, yes, that is something that would make completely sense. There is already research ongoing by our group and also other groups that are trying to develop also data sets of outstanding example of structures from the past and use these to inform the generation of new structures. And this is, in fact, we were mentioning Nervi, but obviously there are many other famous structural engineers and projects that definitely would be extremely helpful to have in a data set in such a way that it's possible then to learn directly from these projects, understanding how these master builders and master designers from the past were able to go beyond these more conventional approaches and try to use them in order to inform the design that we can do nowadays. For example, extracting certain principles from these outstanding projects and then try to reconvey this principle into the design of new structures nowadays. So definitely that is something that is especially relevant. For example, now we are in the process of starting a project that is about creating a data set of bridges, mostly outstanding bridges or very relevant bridges worldwide. And what we are doing is we are collaborating here with a colleague here at TUM, Professor Angela Dai, that is working in 3D reconstruction using machine learning. And the idea there is to be able to develop a data set and train a machine learning model that is able then to generate structural models of bridges that are presented to the machine in the form of pictures. So from the pictures of these bridges, then the machine learning model is able to generate at once not just a 3D model or a wireframe model of the form of the structure, but literally a structural model in equilibrium. And this will be using these methods that I was showing before. And this, again, is also to be able to extract certain principles and then being able to have, once we have these data sets, the hope is that the machine will be able to use this principle to inform also new structural design solutions.
One more question? Yeah.
I'm sorry that I let you
thanks,
come to
Pierluigi.
the podium.
In seeing this work, I think back to history class and learning that architects such as Antonio Gaudi and designers and artists and craftspeople of the time were part of a reaction to industrialization. And whether it's true or not, and the idea or the question that I have is still there, which is to say that, do you think that this effort is a reaction? Do you place it in a category of reaction to the way that optimization seems to be the more prevalent way of utilizing technology like this? And if so, do you see it as a way of being crafty? That would be the way I would put it. Thanks.
Yes, thank you very much. Also, a very nice question and very interesting topic. Definitely, there is somehow a sense of reaction in what we develop. We try to not too much to question how the tools are used, because obviously also being able to use these tools, computer for optimization, is a very relevant topic. But somehow the idea here is also to see to which extent we can really make use of these tools, not just for the specific phase or parts of the design, but also in a more creative way, which means we had the idea, and then we believe that the tools nowadays, computational methods, are not used as they could be used, and we can embrace these methods and tools for many more tasks and in a much more broad way in the design process. Definitely the use of the computer in structural engineering, as it is conventionally done nowadays, is very much about speeding up certain calculations and try to develop efficient solutions, but it's very much rooted towards finding a very specific solution out of many. And the way how this is done is very often starting from a predefined starting points that itself can be questionable. So what we try to do is to make a step back and see how we can use these tools somehow. Also, what was expressed in this quote by Musmechi, on how we can use to explore different structural solutions, and then potentially afterwards go into the optimization. But in the first phase, in the conceptual phase of the design, when the design itself is not fixed, these tools are very, very relevant and useful in order to explore, to help the human designer to explore solutions as they would not think themselves, because very much possibly even biased by their own experience. So in this regard, yes, it is also a way to bring very much creativity and maybe crafts into into the process. On the other hand, design, it's about creativity, and also when it comes to bringing to these more technical aspects, there is very much room for creativity.
Okay, I think with that, it's time. Let's thank Pierluigi for his very informative presentation.
Thank you. Thank you very much.